The hidden hurdles of PTP deployment. My name's Kevin Salvage. I'm the Sales Engineering and Technical Marketing Manager for Leader Electronics of Europe, based in London in the UK. And if you have any questions concerning this presentation, any Leader or Fabrics products, or any general broadcast test and measurement techniques, please don't hesitate to contact me on the numbers currently displayed on the screen. The hidden hurdles of PTP deployment. Is it the solved problem in IP media that people claim? Precision Timing Protocol, PTP, is often presented as a solved problem in IP media infrastructures. Select a grandmaster, confirm the lock, and move on. In practice, many live production systems are operating on timing assumptions that are fragile, poorly monitored, and only exposed when something goes wrong, and that is usually on air. For those who've joined us before, or watched any of our PTP presentations, you'll know that you should not use domain 127. Designing a PTP network around domain 127 is strongly discouraged because it undermines interoperability, predictability, and long-term resilience. Domain 127 is frequently used as a non-default, vendor-specific, or test domain, and some devices reserve or treat it differently internally. As a result, behavior can vary between vendors, firmware versions, and profiles, increasing the risk of silent misconfiguration. Troubleshooting becomes harder, as assumptions made by engineers and monitoring tools often default to domain 127. In hybrid or multi-vendor environments, domain 127 can bypass expected predictions, mask timing conflicts. Robust PTP design relies on conservative, well-understood domain usage, not edge case values. PTP is locked, so why did it fail? In this presentation, we're going to challenge the notion that PTP deployment is done once, devices report lock. We're going to reveal the hidden hurdles that routinely undermine timing stability in SMPTE 2110 environments, including network asymmetry, packet delay variation, switch behavior, boundary clock interactions, and vendor-specific interpretations of the standard. These issues rarely announce themselves clearly. Instead, they manifest as intermittent video artifacts, audio phase drift, or unexplained system instability that is notoriously difficult to diagnose. The comfort of green lights. Green indicators are reassuring but often misleading in PTP systems. A grandmaster being selected and followers reporting locked only confirm participation, not performance. These binary indicators say nothing about timing margin, stability, or proximity to failure. PTP behavior is inherently analog, with time error drifting gradually under congestion, asymmetry, or load before a visible fault appears. Relying on lock status creates false confidence, masking degradation until audio drops, video glitches, or sync is lost. The danger lies in treating synchronization as on-off, when in reality it requires continuous monitoring and supervision to ensure reliable live production. The invisible enemies of PTP. PTP rarely fails without warning. It degrades quietly under conditions that are easy to overlook. Packet delay variation introduces random timing noise that slowly erodes accuracy. Network asymmetry breaks PTP's core assumptions of equal path delay, creating consistent but hidden time offsets. Microbursts and transient congestion stress boundary and transparent clocks, increasing resident time and jitter. These effects accumulate as a rising time error long before devices report loss of lock. Because most systems monitor only binary status, PTP appears healthy, while timing margins disappear. This is why PTP fails silently first, and only falls visibly when production is already at risk. Your network is part of the clock. Boundary clocks and transparent clocks. What are the differences? A transparent clock is like a fan-out distribution amplifier. It puts out a new signal based on the input and adds the time correction field to null out the transient time in the switch. All sync data still goes through to the switch to the source. Boundary clock is like a reclocking distribution amplifier in that you get a new PTP signal on the output, but all sync data is between each switch port and the follower, not back to the source. The boundary clock locks to the source northbound and each follower southbound. Each port starts a new PTP sync session. Each sync session is locked to the switch input PTP sync session. So what does this look like? So here in the top left, we have our PTP grandmaster, which is connected to the boundary clock switch. And other devices connected to that switch receive their messaging. The boundary clock switch is also connected to a transparent clock switch, as you can see here. So the boundary clock is a follower northbound and from the grandmaster, and a leader southbound to the follower. And PTP synchronization is between the boundary clock and the followers. The transparent clock then adds the correction factor. So all devices that are followers connected to the transparent clock receive the messages with the correction factor. Switches matter more than you think. In PTP systems, the network is not just a transport layer. It is part of the clock. Switches directly influence timing accuracy through delay, jitter, and queuing behavior. Boundary and transparent clocks behave very differently under stress, and poor selection or configuration can introduce hidden timing errors. Common pitfalls include incorrect profiles, overloaded clock functions, and mismatched quality of service. Under load or during failover, switches can amplify packet delay variation and asymmetry, rapidly eroding timing margins. Being merely PTP aware is not enough. Switches must be designed, configured, and monitored for deterministic timing performance in live production environments. Multi-vendor reality checks. Standard compliance does not guarantee identical behavior in a multi-vendor PTP environment. Devices may implement the same profile, yet differ significantly in filtering, holdover strategy, and response to network stress. These differences become clearly visible during grandmaster elections, failover events, or degraded network conditions where timing behavior can diverge unexpectedly. Some devices recover gracefully. Others introduce step changes or prolonged drift. Assuming uniform behavior because systems are standards compliant creates hidden risks. In real deployment, understanding and testing how different vendors behave together is essential to maintain stable synchronization in live production environments. To assist you in understanding the performance of your PTP networks, we've created a PTP system commissioning paper, which details a series of grandmaster changeover tests for PTP systems in IP media networks to ensure that your system is robust and reliable and can withstand all of the challenges it will face operating in a live production environment. Having a lab testbed system is essential for successful deployment in IP systems, but it's highly unlikely that your testbed system will scale to the same size as your broadcast facility. So you need to ensure that your test procedures can simulate your actual system. It's also recommended that once your IP media network is operational, that you don't sort of just let your testbed system become decommissioned, because it's absolutely vital for testing software updates and for testing new products that you're planning to implement. Many vendors in the telco world are reporting that following mergers and acquisitions, products they originally purchased have been end of life by the new owners of the company. And that although claiming the replacement product is an identical like fit, when they actually come to test them, they find that they do not perform in the same way as the original product. So therefore, ensuring that your testbed system remains fully functional and operational is absolutely vital to maintaining the health of your IP media network. Hybrid SDI IP facilities introduce further risks. The coexistence of legacy reference signals and PTP can create false confidence, masking underlying degradation in the IP timing domain. How SDI hides degrading PTP performance. In hybrid SDI/IP systems, legacy SDI reference signals, black and burst or tri-level sync, can mask underlying PTP instability. Devices may continue to lock to SDI while quietly relying on PTP only for alignment or future switching, giving the impression that timing is healthy. As performance degrades through rising time error, packet delay variation, or asymmetry, nothing visibly fails at first. Video remains stable because SDI provides a deterministic point-to-point reference. Meanwhile, audio, metadata, or IP-only paths may already be operating close to tolerance. This creates a false sense of safety. Dashboards now show PTP locked. Picture looks fine, and operators assume that the system is resilient. The problem only surfaces when SDI is removed, a failover occurs, or load increases, at which point the accumulated PTP issues become immediately visible and often catastrophic. In short, SDI doesn't fix PTP problems. It delays their discovery, pushing timing failures to the most operational critical moments. The early warning signs. Early PTP and SMPTE 2110 failures rarely occur as sudden loss of lock. They surface as subtle warning signs, rising time error trends indicating degradation, timing margin, long before devices declare a fault. Increased phase noise and wander reveal underlying network congestion, asymmetry, or boundary clock stress. Audio often becomes unstable before video, as it has a tighter tolerance to timing errors and exposes sync drift sooner. What operators usually miss is relying on binary lock/unlock indicators instead of monitoring time errors, behavior, trends, and correlation with network events. By the time alarms trigger, the system is already failing. From status to supervision. Effective PTP monitoring moves beyond simple lock status to true supervision. Lock indicators only confirm that a device is synchronized, not how close it is to failure. Time error measurement reveals real timing margin and exposes instability early. Correlating PTP behavior with network conditions, packet delay variation, congestion, microbursts, and path asymmetry. Explain why errors occur, not just that they exist. Measurements must extend beyond the network core to the endpoints where timing is actually consumed. Turning this data into actionable insight means trending, thresholds, and correlating metrics so operators can intervene before sync loss impacts audio, video, or production continuity. Is your PTP system truly fit for live production? PTP compliance alone does not guarantee live production readiness. A system may meet standards, yet lack the robustness needed under real network stress. Designed resilience reflects theoretical capability. Proven resilience is demonstrated under congestion, failover, and abnormal timing conditions. Live production exposes timing systems to dynamic traffic, asymmetry, and operational change, where assumptions quickly break. The critical question is ownership of timing risk. Is it hidden within the network, pushed to vendors, or actively managed by operations? A PTP system is truly fit for live production only when the timing performance is continually measured, understood, and owned, not simply assumed because device reported locked. Rethink your assumptions. PTP should not be treated as a simple signal. You connect and forget. It is a distributed system whose performance depends on every clock, switch, and network path. Assumptions based on lock status and standards compliance create false confidence. Efficient monitoring must expose risk, not hide it behind green indicators and binary alarms. Without visibility of real timing behavior, problems remain invisible until production is impacted. If you're not measuring time error, its magnitude, trend, and correlation with network events, you are not managing synchronization. You are guessing. And in live production, guessing is not a strategy. So to summarize, SMPTE 2110 doesn't forgive assumptions. It rewards engineers who design for predictable, isolation, and controlled failures. This is not just IP video. It is real-time systems engineering.